Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosine River College in Sacramento, California. This video is a continuation of an introduction to graphing the sine and cosine functions. You should have already watched the videos on the base graphs of the sine and cosine functions, amplitude, reflections, midline, vertical, shifts, period, key points, and step sizes. Those are all videos. This one is the final video before we put it all together. And this is a key video to truthfully understanding the entire process. So let's go ahead and investigate this first example here. Let's go ahead and graph y equals 9 times the quantity x plus 3 squared. And then we'll move over to the second one to graph that. But let's graph the first one. So we know that that is just a quadratic. And it's been shifted to the, let's see, left 1, 2, 3 units. So it kind of looks like this. I'm not really going to spend too much time graphing that. It just looks like a right side up parabola. It opens upward. And it's shifted left 3 units. Again, because that's what causes this argument to become 0. Now, let's move over to the second one and graph y equals 3x plus 9 quantity squared. Well, if you notice, y equals 3x plus 9 quantity squared can be rewritten as the quantity 3 times the quantity x plus 3 and quantity, and then squared. And of course, 3 squared is 9. And we still have the x plus 3 squared. And all of a sudden, you see that this function right here is identical to that function right there. So the graph of this function right here is shifted 3 units over, and it's the same picture. So why do they look different? Yet they're the same picture. Well, I actually showcased why they look different. They had a common factor. At least the second function had a common factor I was able to factor out, and it showed the true shift was -3. Versus this, where a lot of people initially think that the true shift is a -9. It's not. You have to factor that 3 off of that x to really find the true shift. And that's critical in trigonometry. You must factor off the lead coefficient on that x to find out what that true shift is. Now that should be a review that should have already been covered in your course, but it's important to review right now. Because this question is different than the next question. Let's answer this one first. What should happen if we graph y equals the sine of x minus pi? Well, this does not act any differently than any other function. It would be like a sine function, but shifted to where this piece right here becomes 0. What I mean by that is it's shifted to x equals pi. So it's shifted right pi units. Oops, units. And that is fairly standard. We know that already. So we know that's going to shift that sine function over pi units to the right. But what about something like this guy right here? Well, according to what we did in the opener to this video, this should be first factored. We should factor a 3 off of those 2 terms here. And remember, factoring is division. So we're dividing that first term by 3, and that second term we're also dividing by 3. And notice what turns this into 0 is pi over 3. So this has been shifted right pi over 3 units. And that's an incredibly important distinction. Again, it's not shifted pi units to the right because this coefficient needs to be factored off of x, and actually factored off of every term within the sine function. That's incredibly important for our graphing process. So here we go with the final definition for what we're going to be doing with graphs. This is the phase shift. By the way, some textbooks use something different for phase shift. I actually followed this for phase shift. I think it's a very nice definition. So for the graphs of y equals a sine of bx plus c plus d, and y equals a times the cosine of bx plus c plus d, the value negative c over b, let me highlight that, the value negative c over b is called the phase shift. And by the way, it's that negative c over b, it's just because the way I write it, y is equal to a sine of bx plus c plus d. If you were to factor that b off of both terms inside of the sine, remember factoring is division, so bx divided by b is x, and c divided by b is c over b plus d. Notice what would turn this into 0 is actually not c over b, but negative c over b. So this has been shifted to x equals negative c over b. And that means the initial point of our graph has been shifted to x equals negative c over b. And so that's how we're going to start our initial point. All of our graphs will start at an initial point, sometimes at 0, if they're the standard graphs. But if there's some type of phase shift, our phase shift itself will be our initial point for our graph. So let's go ahead and just practice finding phase shifts before we graph. Find the phase shift of y equals the sine of 3x minus pi. Well, there's two ways to go about this. I kind of like being long-winded with this. The sine of 3 and I'm factoring off that 3 off of both those terms. So 3x divided by 3 is x, and pi divided by 3 is pi over 3. So this phase shift is equal to pi over 3. It's what would turn this into 0. It's nothing really new to us. You should have seen this when you're graphing transformations of functions, but now we're calling it something new. Rather than a horizontal shift, we're calling it a phase shift with specifically the sinusoidal functions. So the phase shift here, pi over 3. And by the way, had you mechanically computed it from here, negative c over b would be a negative pi over 3, which would be pi over 3. Same phase shift. It's just that for some reason I just have a habit of factoring. I like to do that. I don't know why. And now this theorem just summarizes what I just said. The x value of the initial point for the base period of the graphs of these two trig functions is just x equals negative c over b. So that's just restating what I just said out loud a couple pages ago. So let's go ahead and use that. We're combining two things that we've recently learned. Phase shift and then period and step size from the previous video. It's because they go hand in hand. You can't do one without the other normally. So let's go ahead and do that. Let's state the period. The period of this function is 2 pi over the coefficient of x. So the period is pi. The step size, on the other hand, recall, is just the period divided by 4. Period over 4. So that's going to be pi, because that's the period, divided by 4. The phase shift, well, that's equal to negative c over b. There you go. See, I did it mechanically. Negative pi, negative c, that's c, over b. There you go. So that being done, there's no vertical stretches or compressions, nor is there a vertical shift. So that being done, we can actually graph, labeling all key points, this function. Since there's not a vertical shift here, I don't have to worry about the midline being off of the x-axis. The midline will actually be the x-axis. And I just draw in an x-axis there since that is my midline. And let's see, what are we graphing? The sine curve? Great. I'll just go ahead and scratch out a sine curve. Try to keep it as nice as possible. I'll just go ahead and do this. Well, that'll do. It's not as deep on the right-hand side, so maybe I'll do that again. There we go. Notice I'm trying to demonstrate good graphing behavior. This is what I expect. Good graphing behavior. All right, that being said, the phase shift is our starting point. That's what the last theorem said, is that our starting point, our initial point, is the phase shift. It's negative pi over 2 is our phase shift, so that's what goes right there. That's, again, the phase shift. And then we just move by the step size. So I'm going to go ahead and label my key points using the step size. So negative pi over 2, and our step size is a pi over 4. I often encourage students to get common denominators up here. So the common denominator would be 4, so this is negative 2 pi over 4. It just makes your math a lot easier. So if you're starting at a negative 2 pi over 4, you can always write that here if you want to. You don't have to, but I'm going to. If you add a pi over 4, now you're at negative pi over 4. If you add a pi over 4, you're at 0. If you add a pi over 4, you're at pi over 4. If you add a pi over 4, you're at 2 pi over 4. Notice that our period is pi, yet we did not end at pi. What we ended at was pi over 2. Yet the period actually is pi, because the distance between pi over 2 and a negative pi over 2 is pi. That's a distance of pi. So don't just label the last point as your period. That would be terrible. And a lot of people do it because they have a habit of doing that. You should not do that. Label your initial point, then step sizes. Just go by the steps until you get to the end. Now that we've graphed that and labeled the key points, I'm going to use my ruler here to graph the y-axis, which goes right about here where x is 0. And then once I graph the y-axis, I'll label the maximum and minimum y values. Move that off the screen a little bit. The maximum y value was 1. The minimum y value is negative 1. And that is because the amplitude is 1. There's no actual stretch vertically. And if you want to showcase to your instructor that this continues forever, you could put these little careful dashed lines, and that just tells your instructor, you know, this function oscillates forever. That's what we'd say. It oscillates forever. Now, I just want to recap. I stated the period. I divided that. Period is just 2 pi over b. I divided that by 4 to get the step size. And then the phase shift is negative c over b. Another way to think about this phase shift is that it is what would turn the interior or the argument of your sine function into 0. If you factored a 2 off, what would turn that into 0 is a negative pi over 2. That's your phase shift. All right, let's try another problem. I came prepared with my ruler this time, so let's state the period, step size, phase shift, and then graph. And this is just the cosine function. I'm going to move that down a little bit. So the period here, there's b, and the negative pi over 2 is actually the c. So let me just put c there. Period is 2 pi over b, which is 2 pi over pi, which is 2. So it takes 2 units to go through a full cycle here. That's what that means. 2 units to go through a full cycle. And let's see, the step then, step size, is equal to the period over 4. By the way, this should showcase to you that periods for trig functions need not be multiples of pi. Step sizes don't need to be multiples of pi either. Look at that, step size of 1/2. And then the phase shift. Well, the phase shift, you could either just do negative c over b, or you could do this as the cosine of and divide pi off of both of those terms. If you did that, you would get this. And what turns that argument into 0 is 1/2. So 2 ways to go about it. I'm just doing it kind of a nice way, I think. I think it's a very nice way. So x is equal to 1/2 is my phase shift. I'm moving over 1/2 units to the right. So let's go ahead and graph a horizontal line here. It hasn't been lifted up or lowered down, so no vertical shifts, no vertical stretches. And I'll move that off of the screen so that I can deal with this. There's my x-axis. I will then graph a positive cosine, because again, it's just a regular old cosine. I'll try to maybe distance these appropriately. Just like that. And connect them through. Just like that. That's a pretty decent graph right there. All right, so having done that, that's a regular old cosine. We're now going to plot the phase shift, or the initial point, which is at 1/2. And then the next point is a step size away. The step size is 1/2, so this is 1. Next point is a step size away, that's 3/2. Next point is a step size away, so that's 2. And the last point is a step size away, so that's 5/2. The distance between 1/2 and 5/2 is actually 2. So our period for this function is actually 2. And we do want to graph the y-axis. That would be a 1/2 unit back. So I'll just graph the y-axis right here. Very often you do have the x or y axes kind of off to a side. I will label the maximums and minimums. Again, because it's 1 times the cosine of x, there's no vertical stretch or compression. The maximum and minimum will just be 1 and -1. And then if you want to showcase to your instructor that you know what's up, just continue this graph if you want. Depends on what your instructor asks. They might want 2 cycles of this or something like that. But that is the graph of cosine of pi x minus pi over 2. These are great methods for graphing trigonometric functions. They're actually really good methods for graphing trigonometric functions. And now that we have the phase shift sort of down, we're going to go ahead and exit this video. And in the next video, we're going to put it all together. We're going to have everything all at once. This is like what you're going to see on an exam in trigonometry, when everything's put together at once. This type of problem, likely no. But the bigger problems, totally.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.